Welcome to the Empowering Tomorrow's Automotive Software Podcast, brought to you by ETAS, a single source of cutting-edge software and hardware solutions that make automotive embedded systems safe, smart, secure, and sustainable. Each episode, we'll be joined by ETAS and industry experts to discuss how electrification, automation, and connectivity are impacting the automotive industry. Now, sit back and enjoy the discussion.
Hello, everybody, and welcome back to the Empowering Tomorrow's Automotive Software Podcast. I'm your host, Zane Pelletier, and today we're talking about AI-guided embedded fuzz testing for automotive modules. Today I'm joined by Irina Nicolai. She is a research scientist with the Bosch Center for Artificial Intelligence, and I'm going to pass it off to her to tell you a little bit more about her background.
Hi, Zane. Hi, everyone. Thanks for having me today. Yeah, about my background. My background is in computer science, and I'm a research scientist now with Bosch Research. My research mainly focuses on AI and cybersecurity, going into both directions. So, kind of how do we solve security issues of AI models and AI deployments, but at the same time, also how do you solve classic cybersecurity tasks with AI? And I guess the latter is going to be part of our conversation today as well.
Perfect. Thank you for joining, Irina. So, jumping right into it, I'd like to introduce the topic a little bit. So, we're going to be talking about embedded fuzz testing, which has been a topic here several times before. But for anybody who doesn't have a background in this area, essentially what we're doing is we are talking to embedded devices, in this case, mostly automotive controllers. And what we're doing is we're sending carefully crafted pseudo-randomized input to the protocol interfaces that are on these embedded devices. And what we're doing is we're trying to monitor for adverse events, whether that is a failure to respond to some known good message, maybe some other program that's running on the device that has some kind of watchdog timer that's getting triggered, or there's some other adverse condition based on what the application of that device is. We're trying to monitor it while we're sending these inputs, and we're trying to see if we can trigger some kind of software bug or hardware bug on the device, which could indicate either an issue with functionality, safety, or in many cases, a security issue. So that's the goal of fuzzing.
So Zane, kind of by now, I think fast testing has quite a little bit of a tradition and has had quite a bit of impact when it comes to kind of application testing and PC software, I want to say, with many bugs in open source or closed source programs being found this way. What's the main difference when you're trying to fast test embedded devices versus, PC software?
Yeah, definitely. That's I think a big topic. A lot of people ask that initially. So I have done fuzz testing of both embedded devices and more traditional IT software and network devices. And I would say for embedded controllers, the primary difference is the reliance of the data that the controller is sending on safety functionality. So for a lot of these controllers, they are embedded within a vehicle and they're responsible for certain actions that the vehicle takes. For instance, braking functionality. Sometimes it's other features that have to do with acceleration of the powertrain. So a lot of these things, if there is an adverse event with the controller that is responsible for those things on the vehicle, it usually becomes a safety issue. And the difficulty here, I think, is the general abstract nature of some of these diagnostic requests that are being made on the controller level. There are a lot of proprietary protocols and messages that are being sent that are not well defined within the standards that these devices are using. So fuzz testing it is especially difficult because we're looking for an even smaller needle in the haystack. There's a lot less that is known about these devices generally, and they're usually very dependent on these processes to operate.
Got it. And are there any kind of technical challenges to fast testing embedded software?
Yeah, definitely. So I would say that every controller is different. And that is a huge problem that we come up with because every time we start doing a new embedded fuzz test, we're basically starting from level zero again. So we are building up our understanding of how the communication protocol is working. And that's essentially that's very difficult because of the nature of fuzzing. It's pseudo random, so you essentially just have to start the test and wait until it finds something randomly, essentially. So you're relying on entropy to find the issues for you, which is not a very efficient way of finding things, I would say. But it's the only way to have comprehensive coverage in some cases where a lot of these inputs are not defined by a standard structure. So this idea of finding bugs in the basic software stack, for instance, of a controller module, is very difficult, and you have to consider time constraints and also hardware constraints of the physical constraints of the testing. Usually, you have to run these on multiple devices, and sometimes these devices are prototypes or one-offs. So having lots of hardware available to you to perform this type of testing is also difficult. So there is a lot of issues there with regards to efficiency overall.
Right, and kind of resource constraints, it sounds as well.
Certainly.
You mentioned testing brakes or other modules that are on cars or from cars, right? And you mentioned safety implications. What kind of failures can one expect to find in embedded and kind of automotive software?
Definitely. So that's a great question. I would say the most common type of failure that we see is some type of denial of service. So completely taking the diagnostic functionality of the module offline, rendering it unresponsive to other modules in the vehicle is a very, very common one that we see, at least for a small period of time. So this could take the form of either sending a message that crashes some piece of the communication stack, or sending a legitimate diagnostic message that isn't supposed to be able to be processed without security authentication on the module. So here you can see if there are some security flaws in the way that, for instance, diagnostic unlock is implemented. You can send a message such as ECU reset, which causes the ECU to do exactly that, to completely reset and reboot through the boot process. And that will render it unresponsive on the network as well. So you kind of have to think about what the module is doing on the vehicle, what it's supposed to do in its normal functionality. But essentially, you can kind of start to see how this could be an issue, especially on a network where a lot of these modules are supposed to respond in a very short amount of time, sometimes as low as 5 milliseconds to 20 milliseconds. Having even a second of downtime is a very, very long time on a network like this, especially when you're dealing with automated driving, ADAS, and things like braking systems.
Right, that indeed sounds very dangerous, and I wouldn't want it, happening on my car, right?
Definitely not.
So then, can you tell us a little bit about how you came to the idea of using AI for ECU testing?
Definitely. Yeah. For that, we're going to have to go a few years back. I was originally working on the fuzz testing tool that ETOS develops, CycherFuzz. And we were running into a lot of common issues that we saw on a lot of different modules that we would work with. So we would see the same issues across the board. And usually we would find some of these same issues in modules that were in the same vehicle architecture or even supposed to be on the same vehicle. So what this led us to believe is that the bugs that we were finding were so common due to their origin, I would say, in a base layer of the software that was being used everywhere throughout the vehicle. So all the different modules, regardless of supplier in some cases. So the idea that we had initially was to try to map out the issues that we were seeing on a certain vehicle architecture, a certain set of modules, or even a certain supplier, and try to train some type of model. We tried various machine learning methods originally to try to train a model that could be aware of common historical issues that we've seen before. But not only that, also to have knowledge of being able to understand the threat model itself for these types of in this case, CAN controllers on a CAN vehicle network. And so the idea here was to build a heuristic that we were able to use to apply to the future so that the system wasn't actually fully random. We were still fuzzing pseudo randomly, but we were guiding it through the process using historical data.
Yeah, I think it's worth also mentioning that pretty much for fuzzing, what one would want in a test case is one that follow like a test case that follows the protocol closely enough so that it can actually be processed, right, and parsed. but you don't want all perfect and kind of like usual messages, right? You do want them to be a little bit faulty or incorrect, and just incorrect enough that they can actually explore those border, right, and like cases, right, those edge cases in your system and find, right, those failures.
That's an excellent point. Yeah. We're looking for, I've heard it explained like the gray zone. You have completely white test cases that are 100% valid and good and can be processed by the system normally. And then the black test cases, those that are not, that are completely wrong, right? And yeah, exactly as you said, we're looking for those that won't get thrown out immediately when they're being processed. So yeah, that's an excellent point as well. And so our idea here was to develop a system that could get close. It could try to mimic some of the same messages it was perhaps already seeing on the network, but modify and manipulate slightly some of the fields, but in a strategic way so that we could start to map out. There was a larger issue. Can we refine what messages are causing that and in what circumstances, essentially? So yeah, with that, I think that's a really good background on fuzzing in general and why we need to use it for automotive controllers to be able to find issues, especially in a security context. So I know that we've been working for a while, Irina, on this project, but let's go back to maybe our initial discussions on what the architecture was to look like for such a system. You know, I know that you have more expertise than I do in artificial intelligence and being able to formalize these systems. What considerations when I first brought this project to you did you have? And I know that we went through several different iterations of this, trying different things. I know I started with a general adversarial network, and then we started to lean towards other implementations of this. And then, of course, in that time also, I would say that the technology and the systems available to us have changed a lot in the last 2 years. So, yeah, can you walk me through what you were considering when we brought this to you?
hmm Yeah, for sure. One of the most common ways I want to say of using AI for fuzzing is indeed to do the test case generation step that the fuzzer would otherwise do on its own. And again, under these constraints that you want test cases that are good enough but not great, so that you can actually reach the depth of your software and trigger crashes. But kind of people have tried to use AI in other steps of the fuzzing process previously, and maybe not all of these approaches were as promising. So I think together we've mainly focused on this idea of generating new test cases. As you mentioned, basically initially you had considered using GANs, right? So generative adversarial networks, which pretty much do a cat and mouse game, right, between two models, right? You're training a model that will actually become your test case generator, and you're training a secondary model that is trying to catch the first model, or rather distinguish real test cases from test cases generated by the generator model. And you kind of know that the generator has won when the second model, the discriminator, is actually not able to distinguish them from real test cases anymore, right? And then kind of you get this generator that is indeed in a way capable of speaking, I want to say, the protocol language that you're aiming for, right? So in this case, CAN protocol. But what happens with GAN models is that they're sometimes kind of a little bit difficult to train. And as you mentioned, also with like recent advances in neural network architectures, we've also kind of tried to switch from GANs to the more recent transformers. Yeah, transformers is just a fancy name for the model architecture that's basically used for models such as ChatGPT and the GPT family in general these days. For our case, it was the most adapted to use what's called a decoder transformer, which is exactly the family of models used by GPT. But I think in our case, we're going for a smaller size transformer than what's used in large language models, just because the CAN protocol does not have as much complexity as human like natural language, right, would. So I think with that we were already kind of aiming for the most promising use, or one of the most promising usages of AI for fuzzing. And with the use of transformers, basically that put us in, I think, in a good position to be relatively state of the art, or actually state of the art in terms of a few things. Transformers, for example, do not have the same training issues that GANs would have. So which means that you are able to kind of train models relatively faster and more reliably. So kind of pretty much you save also some of your development time. Now, in this idea that kind of you train a model to speak the protocol that you want it to speak, remember that we're trying to speak that protocol almost correctly, but not super correctly either. And in our case, to achieve that, basically, if you train a transformer strictly on clean CAN messages, like the regular communications, then this is what that model will generate in the end. So then for our case, what we did is that we used data that contains some vulnerabilities, right, from previous findings. So in that way, basically the model is able to speak CAN, but just a little bit faulty and is a little bit biased towards types of faults in the messages that have proven to work well in the past to find failures in modules. Yeah.
Yeah, that's an excellent overview. I really like the comparison that you're making to ChatGPT. I think because almost everyone listening to this most likely has had experience with that. So that's a really great way of framing it. It's essentially the ChatGPT of CAN models that also has context on vulnerabilities that we found. So that's I think easy way to think about what we're attempting to achieve here. I guess my next question for you is, so I know we went through quite a process of trying to pick. I know that you have developed this actually specifically for this application. So when you went through and you tried to pick, I know there are several libraries available here. I think in this case we were using Python for building this out. Why did you select certain libraries for this? And maybe could you talk about the selection process there? I know initially we used TensorFlow and then we moved to PyTorch. So maybe you could go through some of the considerations that we had to take into account when actually programming the system.
Right. So I think it's fair to say for a lot of machine learning applications, kind of Python is now, and definitely for machine learning engineers and data scientists, Python is pretty much the language of choice these days. Because it's easy to use, but also because a lot of the toolboxes and libraries, the ecosystem for machine learning, it has been developed for Python. So that's where you'll get the best support. And at the same time, I want to say TensorFlow and PyTorch are two of the most commonly used libraries and most popular when you're working with neural networks. And it's true that kind of initially we were mainly using TensorFlow, and at some point we proceeded to migrate the entire code base from TensorFlow to PyTorch. And this is pretty much to account for the fact that I think these days there are indeed, so the community has shifted towards PyTorch. Personally, I don't necessarily have a preference between the two. I kind of like them both, and they're, I want to say, relatively equivalent in terms of what they offer. But for our case, we were also considering including some external dependencies and additional libraries that existed, and those were mainly developed for PyTorch, and that was for us the reason to switch. Outside of that, in order to not have to do any neural network architecture kind of manual selection, because this is quite lengthy and can take quite a little bit of manual effort if you do it by hand. We've also used RayTune to do automated hyperparameter tuning. So now pretty much your neural network architecture will adapt a little bit to the training data set that you have.
Wow. Yeah, that makes a lot of sense. I do really see, for certain applications, I think using certain libraries is a good idea for the tools available to you. But that is something that I don't think that I consider very often when I use specific libraries to either build out tooling or use it for one-off applications. Is how supported is this going to be by the community in the future, especially if it's an open source project? Are there things that I'm going to have to go back in and manually implement or change if I want to come back and use this? And how is its ability to, I would say, adapt over time with changes to our understanding of the best ways to implement things? So that's definitely, I think, very difficult to predict, but I definitely saw an improvement there when we made that shift to be able to adapt to and account for some of those things. So at this point, I think we have a good understanding of what it looks like from a technical perspective, how this thing was built. Maybe now we can go into a little bit of what we tried it on and how we were able to evaluate if this was actually helpful for us in this kind of context. So, just to give some background on this, we actually initially had to develop a threat model for the CAN network within the vehicle, and also specifically the application layer of that in-vehicle network, which is known as Unified Diagnostic Services, or UDS. At this point in time, this actually wasn't well established in the literature. We had gone through several other papers that detailed both fuzz testing, evaluating the security of this diagnostic protocol, and we weren't really able to find anywhere a unified threat model that showed all of the threats to this type of network in a way where it divided out each of the layers of the stack in terms of the OSI model, and looking at different facets of the protocol itself. So that was actually some of the upfront work I think we had to do that had nothing to do with actually implementing the model itself, right? And then following that, we actually had to go out, and I think a lot of people nowadays, especially I think management level people, usually just say, "Oh, we have to implement AI. We got to add AI to it." It's like the new buzzword essentially. To a lot of times, it's synonymous with having efficiency increases and improving the way that we're doing things. But I think that part of that is not usually taken into account is the fact that all of these systems rely on a lot of really good quality data that is pre-labeled by people that are collecting it and categorizing it and looking at what the data actually means prior to even implementing and training some of these models. So I think that process in and of itself took a very long time to achieve, for us at least, because we had to do many fuzz tests, and then we had to go in and look at what was wrong. We had to categorize it, we had to label it, and we had to do this for a ton of different components. I think at this point we've actually collected a total of almost 50 million test cases that have been executed that we had to go look at, and out of that there are hundreds of thousands of failures that humans had to go and look at and figure out what was going wrong there. So yeah, that was definitely a very grueling part of the process, let's say. So our idea here was to create a testing setup. And once we had that testing set up, we wanted to prove this out. So essentially what we did was we went and we found some modules. These modules we actually acquired usually for researchers in the automotive realm. Your options are either the company approaches you and asks you to take a look at their modules or their vehicle. You can go to a junkyard and you can start pulling them out of vehicles that have been wrecked, or you can go on eBay and you can try to find modules off of eBay for people that are parting out, again, vehicles that are wrecked. So that's exactly what we did. We went on eBay and we found several modules from the same type of vehicle. It was actually the same vehicle trim, same model year, and we hooked them all up into kind of a skeleton of the automotive network. And then we went ahead and we did traditional fuzzing on all of them to try to figure out what vulnerabilities existed on the system that we could find. And luckily, we chose modules that did have vulnerabilities, and it turned out that a lot of them had the same types of issues that we were seeing over and over again. So I think we kind of lucked out there. To be honest, it could have not been that way. But we were able to acquire modules that did have issues and that had very consistent issues at that. So I think you can attest to this, Irina. It was a very long process of us going through and collecting data and then labeling it and getting it into place. And even after we had everything and we had our system set up, we did have to go back in and tune things a little bit, because the output I think that we were getting was not quite what we wanted. And I think it was a little bit, in some cases, it was either repetitive or the input was not riding that fine line, that edge case that we were looking for. So maybe, Irina, could you tell us a little bit about, I know hyperparameter tuning and some of the other terminology you used is kind of heavy on the jargon a little bit. Maybe you could demystify that a little bit for listeners who've never done that before, or who are not working at a very deep level with some of these applications all the time.
Sure, but maybe first, I want to answer kind of your point on the data collection, right, and the effort that goes into that, right? So I think with now AI being relatively, more commonplace used in the past decade or so, it's a little bit like the running gag of AI practitioners that, you spend 80% or more of your time doing data collection and cleaning and pre-processing and all of that. And even with the what we know, right, the experience we have collectively, right, as humanity over the past decade, I think the effort that usually goes into the data collection is still very much underestimated and often enough kind of underestimated by companies or maybe management teams, right? And we've seen that in this case as well, pretty much kind of hands on. But definitely for everything that is AI, kind of the quality of the data and the effort that you put here in the data collection is actually what will pay off because no amount of modeling or machine learning that you can do can overcompensate for poor data quality, right?
Right.
And in our case, it also a served as a guidance, right? Because basically the threat model that you developed pretty much tells us what we should be focusing on at the modeling steps. So like what it basically defines the requirements of what the model is should be able to create as test cases, right? And what is the expectation. But on your other point regarding hyperparameter tuning, so what happens is that when you're training a machine learning model, there are kind of training that basically means finding the right values for certain parameters in an automated way based on your data. It's pretty much kind of really just fitting mathematical functions to match your data. But those on top of those parameters that you're kind of fitting automatically, so that's the basically the training part. Your model usually and the entire training process has additional parameters that you're supposed to pretty much kind of set by hand. So these can mean, maybe the size of your neural network model. This can pretty much tell you, I don't know, how long you're training and things like that. And those are things that are not always so basically that you cannot do automatically based on the data per se. And these are the ones that are called not the parameters of the models but the hyperparameters, so they're kind of like at the next level of abstraction. And historically speaking, maybe kind of like 2 decades ago, people were using a lot of time to tweak these models, these parameters by hand. But luckily, by now we kind of have and the knowledge and the tooling to do so automatically. And yeah, basically this is what we used in this case because I want to say there's no kind of virtue or anything like that by to tuning these parameters by hand. And being all of us in an automation field, I think whatever can be automated should be, and it pretty much adds to the effort gains, right, that we're hoping to, and the efficiency gains that we want to actually get right from these models, right?
Definitely. Yeah. Well, thank you for that. I think that's very helpful. And I, at the end of the day, it always strikes me, I think people put a lot of weight on how far this has advanced. And I think from an external perspective, it kind of looks like a magic almost, right? But in the end, it's all just math. In the end, you're all just trying to do some of these same statistical tests of what is most probable to come next, in a sequence of things, and that's ultimately what we're trying to get to here. So it always helps to kind of take a step back and look at, with all of these terms for things, what does this actually mean, and why are we trying to do these things. So I don't want to dive too deep into our results from this because I do think they were promising, right? I think that after all of this time, us working on this project, it was definitely worth it. I will say that we actually did reserve one of the modules that we looked at. And what we did is we didn't fuzz test it at all. Actually, we just took the data from the other 4 that we had set up, and we went ahead and we trained the model with that data. We gave it the information from those vulnerabilities that we were seeing, and we went ahead and did some of that hyperparameter tuning on that model to try to get it to be the best shape it could be. And when we went ahead and tested it against the 5th module, essentially high level, what we found is that you could find all of the same things that would take you weeks on the modules before. And this is weeks of trying randomized input to try to find these things. You could get essentially the same coverage from a model that already had knowledge of what issues were historically on the vehicle in a matter of minutes instead of weeks. So it was almost 100 times increase in the efficiency of finding these things. And I think that's by virtue of the fact that we had trained this model to know a lot about CAN, and not only know a lot about CAN, but know a lot about the issues that were present on this specific vehicle, and I know there's also something that we're working on right now, Irina. I don't know if you want to go into your application of I always just refer to it as model patching, but we do have kind of an issue here where since these modules are so unique and so proprietary, there are issues that we will most likely find on certain modules that we will have found nowhere else, right? So what happens when we want to take this base model that we've created that is generically able to find things on the network and apply it to one specific case? Can you talk about kind of how that works and what goes into implementing something like that?
Sure. So what we are planning to do next is what's known also under the name of fine tuning. So let's consider that our base model that we trained so far with, kind of existing test cases from previous logs and test runs. Basically, this is what we would call a pre-trained model. Kind of a pre-trained model is you can find these and download them also from the internet when it comes to, for example, natural language. So it's really just a model that is trained quite generically. Again, this is what happens with a lot of large language models. So, for example, even ChatGPT is trained to chat to humans, right? But it's not necessarily trained for a very specific task, like, I don't know, maybe crafting a workout plan for you or something like that, right? But then if you want to take such a generic model and then adapt it to a very specific task, that's something, that's called fine tuning, and that it can be done provided that you have a good pre-trained, like a good base model. It's something that can be done, the specialization, with very little data. So there's a lot to gain in terms of efficiency if you have like a great base model that afterwards you're trying to specialize to a given task. So here the idea was to use the general CAN model as a pre-training and then to kind of adapt it either to different types of vulnerabilities or potentially, as you mentioned, to different types of providers or different types of modules, right? So naming this pretty much as seeing this as a specialization. And this, again, is a relatively standard setup for many tasks. So having pre-training and fine-tuning as two separate steps. But here we tried to, or we want to do this kind of more efficiently. And for that, we would be using some pre-existing methods. One of them is called low rank adaptation, and the short for that is LoRA. And there is also like a newer version of that that's called DORA. So pretty much what they do in normal fine tuning, you would go and take that base model and actually continue training parts of it to specialize it to the task that you want. But with LoRA and DORA, they found ways, also it's back to math, of doing those adaptations in a way more efficient way without kind of changing the base model. Is really you have more some shortcuts or like some appendices to your base model that represent your specialization. So then this is something that can be done quite efficiently from a training perspective. This is something that can be also done with, as I mentioned, with very small amounts of data. So that means that, for example, if you wanted to specialize to a specific type of vulnerability, you would not need a lot of data, a lot of failure examples from that vulnerability, and the adaptation would still work. And this is also something that can then be kind of stored efficiently because you would always have your base model that's not modified. And then you can load on top of it different adaptations or like appendices, right, that allow it to behave in a certain way for fuzzing specific vulnerabilities or devices.
Awesome. Thank you for that explanation. Yeah. Again, I think another moment to kind of demystify a lot of the processes that I don't think I personally understood in the past, and I think a lot of other people maybe struggle with. But yeah, that's definitely, I think, very necessary, especially with this type of application. So I know that we're hoping to continue researching this topic. I know that we're hoping to do some future experiments. Hopefully we're able to, get accepted into some kind of academic conference and talk about this more. And hopefully this also gets adopted into tooling in the future. But yeah, Irina, I really want to thank you for joining today and really talking about this topic with me. I know that we were able to go through a lot of things. There's a lot to cover here. And I really thank you for bringing in your insight here to talk about how we can use artificial intelligence systems to help us perform some of these types of security analysis on devices that are historically so tricky to fully evaluate. Do you have any closing thoughts about this topic before we wrap up?
So from my side, kind of the work we did together makes me really happy because I think we managed to find a great use case for AI in fuzzing, where I think kind of we've seen more, kind of state-of-the-art fuzzers are actually very difficult to beat with or without AI. But I think kind of with this embedded setup, we managed to find like a setup that's actually quite difficult and where AI can really help move the needle. And as you mentioned, I'm actually really happy with the increase in efficiency, right? That you mentioned, right? So bringing testing time down from weeks to basically hours. I think that's something that can have real world impact, right, for the security engineers and testing engineers who need to do these processes usually. So I'm really hoping that we're going to try to publish as much of our approach as possible, and I'm really hoping that this will be adopted and more people can benefit from it. More generally, I am looking forward to seeing how AI can shape the future of security and safety, maybe in the automotive domain.
Certainly, yeah. And I know that both myself and my team are probably going to be utilizing this quite a bit. And I hope that others are able to get a lot of insight from this and hopefully be able to apply some of these same things to other domains. Well, thank you all so much for tuning in to this episode of Empowering Tomorrow's Automotive Software Podcast. We hope that you found our discussion insightful and valuable as well. If you enjoyed today's episode, don't forget to subscribe on Spotify, Apple Music, or wherever you get your podcasts. Feel free to share the episode with your network and leave us a review. We'd love to hear your feedback.
Thank you for joining this episode of the Empowering Tomorrow's Automotive Software Podcast. Please leave a comment or review with your feedback or what you'd like to hear in future episodes. To learn more about automotive embedded systems and ETAS's capabilities, visit our website at ETAS. That's ETAS.com.